Hi, my name is Nathaniel Jones, and I'd like to thank you for joining this webinar, Large-Scale Modeling of Wind Comfort and Safety Using the Pedestrian Comfort Analysis app by Praveen Kumar and Vijay Mali. This webinar is hosted by the IBIPSA USA Research Committee with the goal to share new ideas from research to the building simulation community. If you have questions during this webinar, please type them into the chat window. At the end of the 40-minute presentation, I will unmute our audience on Zoom for discussion with Kumar and Vijay. AIA Continuing Education Credit is available for attending this webinar. Please email info@aiaeb.org with your AIA membership number to receive credit for attending today's event. And now, I'd like to introduce Praveen Kumar and Vijay Mali. Thank you.
Am I audible?
All right, go ahead.
Hello. Yeah, great. Thank you, Nathan, for the short intro. So first, myself, Praveen, I'm the product manager of SimulationHub, and along with me, my colleague, and Vijay Mali is CTO of CCTech, and both of us are here. We have a background of CFD, simulation, and analysis, and product development things. And I would like to start with what we do and what is our company is. So CCTech is the company. We are about 100 people, 100 engineers and developers. We provide engineering development, software development services, and we also have developed SimulationHub, our own product platform, on which it's web services upon which we can develop and build apps. So through this web services, we have already developed a few apps which are out in the market, and like the Pedestrian Comfort Analysis app and the Autonomous Valve Safety app. These are safety applications which are developed, the vertical domain applications, which are targeted and designed for a specific domain. So we'll go into detail later. So that's about us and what we do. So this is the outline of today's webinar, today's presentation. So first, we will start with what is pedestrian comfort and safety. We'll understand why it is important and what are the different methods to assess wind comfort and safety around the buildings. Right. So, and we'll go shift our gear and move it to the apps, which is Pedestrian Comfort app, and how we are going to assess wind comfort and safety using a case study. So that is the whole idea. So without further ado, I'll jump into the content. Okay. So first, this is the pedestrian comfort and wind comfort and safety. It is a branch of wind engineering, which is dedicatedly to understand the effect of winds around buildings and how it is affecting the comfort of pedestrians or cyclists. So why we should be really concerned about the comfort or safety, right, of pedestrians? Like why we should be concerned about the wind comfort? You can see, right, like shown in the video, there are some local wind speed acceleration that can happen around the buildings and which can cause discomfort, and sometimes it could be dangerous for the pedestrians as well. So it's really important to understand how the wind behaves around the building, and we can take preventive measures to avoid such discomfort, local acceleration of wind around the building. So to understand this, we need to know what happens, what causes such wind behavior around the buildings. So here I'm taking use of a flow around an isolated block or building. So to understand, what are the different flow features or flow physics that happens around the buildings. So when the wind hits the building, it separates at the edges of the buildings and it forms a zone of recirculation at the wing. Okay, and you can see the wind profile, the velocity profile. It increases. The wind velocity increases as we move above the ground level. So the wind velocity hitting at the top region of the building has a high pressure compared to the bottom region of the building. This causes a downwash. So downwash is, amount like large amount of mass of air coming down, pulled down towards the ground. And this downwash, before hitting the ground, it starts, moving upwind and forms a vortex. So this area of vortex can sometimes, accelerate or causes local increase in wind speed near the buildings. So there are similar to downwash. There could be corner effect, wake effect, or this is we are talking about single building, but there could be row of buildings, and which can cause a funneling effect when the wind is being channeled between the buildings. So yes, so these are different effects that happens when wind crosses the building. So let's take an example and what happens in a real physics. That was a block, isolated block, and let's try to see how downwash affected a real situation. So this is a building, walkie-talkie tower. This stands 500 odd feet, and it is in UK. It's in London. So there, the building stand face off to the prevailing wind direction. And what happens is the wind hits the face of the building, and then a downwash occurs. And there are a lot of complaints that have been registered by the pedestrians who walk by the buildings. So it causes local discomfort to the pedestrians, and there has been a number of complaints and that is registered. And these happened because the study of wind effect is not done at the design stage itself. So in the same city, we look at another building, which is smoothly shaped and where there are no downwash effects. It just even in the prevailing wind direction, the flow just around, it flows around the building. The wind flows around the building, and it has a smooth flow where there are no such complaints or no such dramatic wind effects that is happening at the pedestrian level. So I'll have a poll question here. So what do you think? Do you really think it's a good idea to know the wind behavior around the buildings at the design stage itself before the construction happens? Okay, I guess we got the poll ended. Yes, we got the results. Like yes, everyone feels we need to. It's a good idea to know the wind behavior, right? So that we can design the buildings accordingly. So we can avoid late surprises as well. Okay, fine. So I'll move on to the next thing. So now we all feel we should. It's a good idea to know the wind behavior upfront. So what should we do? How do we assess the wind effects, these wind effects, before the construction or at the design stage itself? So there are two large methods. One is the wind tunnel testing, where the scaled down models of buildings and its topographic constructions are constructed. Topographic buildings are constructed and exposed to scale down wind velocities, wind air. So there, these tests are conducted in the wind tunnels, what is called wind tunnel, and probes are installed at certain places to measure the wind velocity and pressures. So when we do this study at large level urban areas, scaling and scaling is a problem. So we need to translate all this data back to the original scale. So that does introduce some errors, and then these probes of this scale can also cause some induce some wind effects, which is very artificial. So the number of probes that can be used are also a limiting factor in this. So these are the drawbacks of wind tunnel testing. So on the other hand, the computational fluid dynamic simulations, where the buildings are simulated at their original scale and original wind speed, and we can see these data are generated at each and every point in the domain around the buildings. So using by solving the Navier-Stokes equation. So this data is available at any time, even after the simulations are done. You can measure the wind data at any point around the building, and all the data is available, like pressure, velocity, and everything. So, what are the downsides of this conventional CFD simulation? Definitely demands CFD expertise. You should know what is CFD. You should know the domain properly, how to run proper CFD simulations, and you should have these simulations are computationally heavy and time-taking and costly. So you need high-power computing resources in your access. So that is one another drawback, and the software, so the commercial codes which are available, that comes with a heavy licensing cost and so on. So here is another poll. I just want to know. Currently, how do you assess wind comfort if you're in this domain? So how do you guys like? Okay. Fine. I guess so. Yes. So these are the results. Like we got a mixed of some one person, like when people like some group of people go for internal study and more on CFD simulations, and few people do not do perform these studies currently. Okay, so now we'll try to see another poll just to make it more interesting. Uh, what are the challenges do you currently face in the current methodology you use, or even what stops you to not to do or not to assess wind comfort? Whether you use the wind tunnel testing method or the the uh, the CFD methodology, or are there any hurdles which acts as a roadblock for you to use any of these methods? Okay, I guess we got some we're getting some responses. Yes. So the results shows mostly all of the above, kind of the time cost factor and the lack of CFD knowledge or the lack of knowledge to use the available technology. Okay, fine. So what we did, we do agree with all the hurdles or the challenges you face in the current method. So in at simulation of what we have done is we taking all these factors into account, we have developed a pedestrian comfort analysis app. So what it does is it does use the CFD technology, but it is designed for architects and urban designers. And you do not have to have any knowledge about CFD to use this app. So it does all the CFD processes like right from cat cleanup, fluid volume extraction, and the mesh generation, and the solver settings or solver and post processing, solver convergence, monitoring, and everything. So all these processes are automated, but not only automated, it is more than that, it is autonomous. So what happens is, let's take the case of cat cleanup or meshing. So the app knows exactly what is the appropriate mesh or cell size that is to be maintained to capture the geometry and also the flow physics happening around the building. So no inputs related to CFD will be asked in the app. So the user, whoever is the designer, the app talks the language of the designer. So just removing the one hurdle, which is the CFD domain expertise. So the second one is the app is accessible on the browser, web browser, and then you can run the simulations on the cloud platform. So it does not use any of your local resources for running the simulation. Okay, so thus we have removed the second hurdle, the resources part. So you do not have to own or you do not need access to those high power computer machines. And then the other thing is in the conventional CFD, when I'm talking particularly about the wind comfort study, in the conventional CFD software, you get what you get out of the software or the CFD simulation is just the wind, the wind velocity plots or wind velocity data and pressure data. But you need to do more than that. You need to get those data and process it to generate something called as wind comfort plot. Okay, so our objective of the study is not just to look at the wind velocity around the buildings, but use this data to understand what is my wind comfort level, right? So you need extra processing or algorithms and codes to do this job. So what we have done is we have incorporated that algorithm and it collects wind simulation from multiple wind direction. So, all the prevailing wind directions you can add and you can combine it with the historical weather data and the comfort criteria. We'll discuss all these things in further slides. So we provide something what we call as comfort plot. Okay, so the workflow of the app is very simple. So the designer uploads the building mass model and he gives some more information about the building or the site, like very relevant inputs like the site location, orientation of the building, and which weather data should be taken from the weather station. So we do provide choice of list of weather stations which are nearby the site location and the user can select from them. And then how many wind directions are to be considered for the study. So once the simulation is, that's it. These are the inputs we collect from the user. And then all the simulations, CFD simulations are done autonomously in the background and the cloud platform. And once the simulation is completed, you get the results, CFD results, and PDF report, which is downloadable and directly you can submit it to the end client. Okay, so now I told you about the workflow, like what the user has to do, but what the app does at the background. So that we'll discuss something about that. So once you have uploaded the model and submitted for simulation, the app assigns a dedicated 36 core cloud machines, compute optimized cloud machine, and then it uses, as I mentioned earlier, the app is built on the SimulationHub platform. It uses SimulationHub web services to do the CAD cleanup, the machine, and the solve convergence solution, and even the post processing also. So if you notice, all these processes are carried out for all the 16 or 8 or 16 or 32 wind directions, whatever you have selected in the app. So all these wind simulations, 32 wind safety simulations are running parallelly, and at the end, you'll collect all the results. It's a mammoth of data, like GBs of data, which is processed and readily available to the user to be able to view it in the web browser, and also the report. Yes. So we have validated the app methodology using a test case, which is mentioned in Architectural Institute of Japan. And this case is case E. It's a building from Nagata. So the building of interest, which is highlighted in the blue color, which is 60-meter tall. So we have this comes around. The surrounding buildings are also modeled as blocks, and we have done this validation study for a number of wind directions. What I'm showing you is for the north wind direction. And you can see the lot of 80 probe locations are there, and for which the experimental wind data is available. And then the normalized data is plotted in the graph shown here. And you can see the blue color, the graph, the curve. So that is the data of SimulationHub, the PCA CFD generated data, which is pretty close, approximately in alignment with the experimental values. So I was talking about wind comfort criteria, right? So wind comfort is really a relative term. So it depends on the activity level, right? So there are different criteria which are specified by local urban authorities, like the Lawson criteria. So each, any criteria you take, it is categorized into two things. Like one is the comfort and the other one is safety. So in the comfort, you see there are different activities like standing, sitting, walking, jogging. So these things, and the threshold velocity is defined for each of these activities. And this is the percentage. The exceedance percentage is that percentage time of the year where it cannot exceed this threshold limit more than this percentage of the year. So for example, let's take distress. Then the velocity anywhere locally should not exceed 33 miles per hour for more than oddly 0.022% of the year, which comes around roughly 200 hours or 8 days, approximately 8 days out of 365 days in the year. So these are the criteria which are specified. So there are different criteria available. For example, Lawson, which is mostly followed in the UK, and NEN 8100 is a Dutch standard. So there are different standards, and all the standards are available interpreted in the app. So user can select based on your requirement. So one such few examples of those comfort plot are shown here. So this is a location in Stanway, which is a tram stop, and you can see it's nearby the shore, and there are some kind of funneling or some local wind effect is happening, and you can see some discomfort areas near the tram stop. So similarly, some other city you can see. So we can generate and get the idea in the urban level scales. Using this app, you can study wind comfort for urban level scales. Yeah. Okay, so here is a short video, 2-minute video. So which shows the usage of app, and on the right bottom you will see what are the stages. So we'll see those stages in detail, but for now I'll just play this video. Okay, so now that was how we use a user typically uses the app, but we'll go in detail of each step, which will be of your interest. So we'll take the case of Empire State Building, and we'll see how we have used the app for doing the safety simulation. So there are some guidelines when uploading the building design model. So you select the building mass model, and then you select an area such that it contains at least one additional street block in each direction. So here we have considered around 1 kilometer, kilometer by kilometer square area, and then the level of detail of buildings depends on how far the building is from the center or area of interest of your buildings. So that's how you can model it as simple blocks when the building is far away from the center building. So the second step, once you have uploaded the building mass model, then you have to select the site location, and based on the site location, the app shows the nearest weather station data, and you can choose the weather station data which is very applicable or appropriate for your site location. So once the site location is done, then this is you have the option to consider how many wind conditions. If you want to have a high fidelity solution, then you go for all the 32 directions. Okay, so if you want to reduce the number of wind conditions, you can go for it. Maybe you can select 8 or 16 or 32. So here, this is called the wind rose data, which shows what are the, based on the selected site location or weather station data. So what are the wind directions, prevailing wind directions, and what percentage these colors indicates the predominant wind speed in each directions. So, okay. So the step 4 is the wind exposure, which is, which decides the atmospheric boundary layer profile. So when the wind comes in contact with the ground surface, so the domains which you haven't considered, the buildings or the area which you haven't considered for the simulation, what kind of wind exposure it got exposed to, what kind of surfaces, whether it is a country, or is it a sea, or it is a suburban kind of thing. So there are some guidelines, and based on that you can select which wind exposure you would like to add. So these are the 4 steps which user does, and what happens in the background is, first step is the creation of computational fluid domain around the buildings. So it will build the computational domain around the uploaded mass buildings, and the size of the building is decided by the app, and it has the algorithm which takes care the blockage ratio is appropriate, and the vertical height of the computational domain is 5 times the maximum height of the building. So these are taken from the best practices and references. So that is fed into the app. So you don't have to provide any input. I'm explaining what is happening in the background. So this is the computational grid for the Empire State, the case which we have taken, and it all these points listed out on the left side is following the best practices mentioned for developed for outdoor wind comfort, flow safety simulations around the buildings. So you can see a minimum of 10 grid cells should be on the sides of the buildings, but we have more than that. The refinements are made on the edges of the building, you can see here, and the Y plus near the ground, and the mesh refinement is appropriate, and it is decided by the algorithm to capture the geometry as well as the flow physics. So these algorithms are fine-tuned after doing multiple, hundreds of simulations and fine-tuned validation studies, and then it is fine-tuned to this. So the algorithm has learned the cell size and things. So the next thing is boundary condition and solver setup. So I explained about the atmospheric boundary layer parameter, right? So this is the formula. It's taken from the ASHRAE handbook. So it follows that profile depending on whether you have selected city or urban or the sea. So these are the input boundary conditions we use for the inlet. It is a boundary layer profile, and the buildings are considered a no-slip wall, and the top portion is a symmetry. And we use open form solver, which is well validated, established in the background for the simulation purposes. So the simulations are done using 3D steady states isothermal simulations, and the turbulence model is realizable KEPS. So the convergence criteria is the stricter convergence, which is typically 1 e power minus 4 less than 1 e power minus 4, and yeah. So once the simulations are done, performed in the cloud, then we provide all the data for each and every wind directions. Here I've shown only up to 16, but we have, for this case, we have used 32 wind directions. So all these wind simulations are done for each wind direction, you can see. And these contours, whatever you shown in this presentation, like this slide, is taken at 1.6 meter from the ground, which is at a breathing level of head level of a standing occupant from the ground. So now we combine all these CFD simulation wind velocity data with the historical weather data available in that site location, and combine it and process it along with what criteria the user has selected to create this wind comfort plot. So here the colors indicate, each class, for example, the red color indicates distress and dosins, as seen in the Lawson criteria. So this is using the case study, we have seen how the app can be used for simulation. And in the further development, this is a work in progress. So we are bringing the effect of how how to include the plantation or vegetation effects near the buildings, and also how to include the topographic information, the terrain part. So that part we are working on, and then you will see in the future development, future releases. Okay, so this is a summary of, like, we are at the end of this presentation. So first we introduced, like, we learned what is wind comfort and how it can be assessed using CFD, and what are the conventional downside of conventional CFD, and how the hurdles have been addressed in this app. And we saw the validation study conducted using the app, and then we went through the steps involved in pedestrian wind comfort using a case study. Yes. So what next? What you can do is, we would recommend you to try out our app. You can log into www.simulationhub.com, and it's in the browser, and then you just open, and you can either request a demo, and then we can connect with you, or you can try it for yourself. You can subscribe. We have a free trial subscription, which provides 32 credits, which is sufficient for 32 wind simulations you can perform. So you can try out and connect with us. And I'm taking this opportunity to we introduce autonomous HVAC CFD. Right till now, we have seen pedestrian comfort, which is outdoor wind comfort, and we have recently launched the early access version it's completely free early access version of indoor thermal comfort, occupant thermal comfort app. So we recommend you to try this app as well, and then feel free to connect with us. Okay, now the session is open for questions.
All right, well, thank you very much, Praveen. This has been a really interesting session. And I want to remind everyone, first of all, that you can get continuing education credit for attending this session by emailing info@aiaeb.org. And also, please, if you have questions, type them into the chat window, and we'll give you a chance to ask those. And while everyone is taking a moment to come up with their questions, I'd like to start by asking one of my own. It's really cool to see, Praveen, that you're doing work on indoor thermal comfort too. And I'm curious if you've looked at mixing outdoor temperature with wind speed. Certainly, it seems like depending on the temperature, we might, find wind to be more or less pleasant. So, is there a way to combine those?
Yes, we are also working on that. But in the current version, only it's isothermal, and it's the outdoor wind is purely isothermal, and there are no thermal effects as such. But what you're asking is really interesting. It is important for urban heat island kind of effect, to study the urban heat kind of effect, outdoor thermal comfort. So that we are working on, and
Okay.
Vijay? Vijay, you would like to add something?
No, I think you said it correctly, Praveen, that it's not only the temperature of air that we need to consider when we want to take the effect of temperature on the comfort. So there are other aspects about how temperature affects the comfort. So urban heat island is the concept wherein it's not only the air temperature, but what happens to even the roads, the building, their surfaces, and how they contribute into the thermal comfort. So we are looking that aspect more deeply rather than just including the temperature of air into the application.
All right, thanks. We've got a question that's just come in, and I'm not sure of the name. The username is V. Brasuski, I think. Do you want to use your microphone to ask your question?
Hey, can you hear me?
Yes.
All right, perfect. I'm just curious, one of the ways that we analyze outdoor comfort is through UTCI calc, where it looks at mean radiant temperature and things like shading and sun path and such. Just curious if there's work being done to include that, or if there's any solar position or shading built in, or if that's just part of a next steps for you guys.
Yes, the UTCI and SAT, set temperature. So that again, goes back to like including the thermal effects in the outdoor. So that is still a work in progress, and we that is in plan. Yeah. When we deal with the outdoor thermal comfort and also the urban heat island application.
All right. Thanks. I have another question. When you're looking at the input data, and I take it that you're taking input data from airports for the most part. Often airports have open terrain conditions, which can change the wind profile compared to the city. And I saw that you are putting in some indication of the terrain types in each direction around the urban location. But do you have like a database of the conditions around each airport, or how do you manage the translation from the airport site to the urban site?
Okay, so the weather data or the weather stations data is taken from the energy weather plus data source.
Mm-hmm.
So I understand, the often the site location or the weather station is a bit far from the site location, and the local wind conditions might be slightly different from the one taken from the weather station. Okay, often airports or things. But right now, like we are providing, the user can also, it is not available for the normal user, but you can contact the support team and you can add your own data if you have that translated data. So you can upload your own data as well, like the wind velocities and what conditions. But currently,
yeah. So currently, the way we handle translating weather data to the local site is, one is you can choose what sort of a surrounding is there. You might have seen in the step wherein he was selecting whether wind is coming from the city side or it is coming from the seaside, so and so forth. So you can select that. So there are some analytical calculations or empirical formulas wherein it helps us to transform the meteorological data or the weather station data based on the conditions. So that is one part which is called as modeling the atmospheric boundary layer. Second is, it is advised that if your building is at, let's say, XYZ location, so you at least model some portion around it. So those buildings will help, because ultimately the wind conditions at the meteorological stations will change because there are a lot of disturbances in between around the building. Maybe topography or buildings are causing it. So we ask user to model a sufficient amount of a surrounding so that the local change of the wind, that effect is taken care in the model. It's not only one isolated building that we should model. We should also model a surrounding around it so that that effect will come into picture.
It's really useful to know. And building on that, as we think about a case where we might be looking at the wind comfort of a campus or a park or an open space in a city, how much of the surroundings do we need to include in order to get an accurate result? Or maybe a better way to say it is, in my surroundings, how close to the edge can I get before my results stop being accurate?
okay.
Yes, Praveen.
Okay. So the general guideline says, to include at least one minimum of one street block around the main center of area, but that may not be sufficient at some times. You need to include more radius of buildings. So it really depends on the kind of height of the building as well. So there is a general guideline, like kind of thumb rule. So 1 or twice the height radius should be like twice the height of the maximum building. So that is the thing. But for the computational domain, that was about the how many buildings we should consider. But for the computational fluid domain, the blockage ratio, the open area should be such that the buildings or the blockage ratio should be less than 3%. So this domain should be really large.
All right. And I want to remind everyone, if you have more questions, please go ahead and type them into the chat. I see you've got a question coming from Andy. Andy, you want to go ahead and ask your question?
Yeah. So I was wondering how much influence changes in terrain have on thermal comfort. Are you able to model that or using digital elevation models for that?
Yeah, it changes a lot. You might have seen that if there is a building very near to the mountain, the effect is far different than when it is there. The terrain is nothing but kind of a blockage to the open air. So accurately modeling terrain definitely affects the comfort criteria. You may need to, let's say if your building is near the mountains, or let's say city is surrounded by the mountains, and let's say city is in desert kind of open areas, you might see the effect of wind in a very different way. So considering terrain is very critical in terms of accuracy of pedestrian comfort, and that is why we are putting some efforts into bringing in the terrain. In fact, in current application also, if user has a terrain profile available with him, he can actually include that in the app and then do a terrain. But we are going kind of one level up, saying that user has given us the location, so why not to use kind of available terrain data and then do that modeling effectively. So to answer your question, yes, terrain affects the accuracy of results a lot.
Thank you.
We have another question coming from V. Brasiszewski. You want to go ahead and ask that?
Yeah, my question is related to the geometry input for this. So one of the big time sinks for CFD analysis is just getting your clean geometry, and used to be airtight and just a headache. Just can you speak to basically the quality of the geometry input that needs to go into your web app, and then which file types are accepted or which software you're generally uploading from?
In fact, we support all type of file types, if I may say so. So I think file type is not an issue, but what we expect is, because these are not a micro level analysis. These are the size of, I mean, the domain is not micro level. We are talking about a very huge area. So we expect user to not to do too much detailing of the building, because the pedestrian comfort is mainly something to do with the orientation of the site and all. So we expect people to just do a mass modeling, a kind of approximate block kind of modeling, so that it is easy to process, or it doesn't take too much time. Doesn't mean that the product cannot handle complexity of the model. It's just that the amount of time it takes and the amount of mesh count it will have. So to answer your question, almost any type of the model, you can say, there is no restriction as such in terms of what file type that you can use with the application.
Does it have to be airtight? Do we have to do pre-processing on the geometry, or there's some simplification?
No, you have to just upload the mass model, the external fluid domain, the domain around it is automatically created by us. So we make the model airtight. If you are asking the question in this means that, can my building have a hole? Yes, it can, but the wind will go through it. So
yeah,
that way,
I'm talking about the massing model. Yeah. So it really needs to be simple blocks that are airtight. Yeah.
Yes. So that, it will just capture the outside area of it. Else it will start capturing, the inside part of the building also.
And depending on the size of gap or leakage, if it is really a leakage kind of thing, so that is handled by the fluid volume extraction algorithm. But if the hole size is large enough, then yes, there it just gives a warning, and the things are added, and you may have to fix it. But talking about small kind of windows or some those kind of small details, you do not have to worry about it. So the algorithm packs it nicely and closes it automatically.
So if you're worried about that you have modeled windows, but there are some cracks, gaps in the windows and the wall, you need not to worry about the that aspect. That the product takes care of it.
I got you. So it's recreating the geometry prior to running the simulation. Okay.
Yes. I mean, I should not say so, but there is a lot of research happening within the company. Also, we have solved almost a lot of the hurdles, but now the clean geometry is one of kind of a requirement. We have solved some part of it, but we are working more on how we can make it robust so that the whole process truly become autonomous.
Yeah. Can you talk about I mean, you talked about the domain size is enormous, and yet we're looking for results at the occupant, which is a person that you said the cut plane's at 5 feet or so. Can you talk about mesh at resolution and the quality of results at having such a large scale? Talk about what guidelines you put into it, or how we can trust the results out of it, basically.
Okay, so the cell size, there are few guidelines extracted from the BEST, like best practices derived for described for this wind flow around buildings kind of simulation. So from there, the number of cells, it is in number of cells, but we have really refined the edges of the, we have maintained the number of cells mentioned in the document, like the best practices for that. And then additionally, we have refined the edges of the buildings. And also we have maintained, if you talk about the ground level, then we have maintained the Y plus, which is like 30. And the cell size is derived, was fine-tuned after doing multiple validation studies mentioned in the AIJ, the website. So they have different cases. So we have taken all those cases, fine-tuned our algorithm, and we have fixed the mesh cell size.
Yeah, to add more on that, if you go probably away from domain of your interest, let's say you have a building. So if you go away from domain of your interest, the cell size you might see a cell size of a 0.1 meter by 0.1 meter, or probably sometimes it might become like a 1 meter by 1 meter if you go far away. But if you go very close, the cell size might be in millimeters. So that kind of a resolution capturing is done to capture the building profile. We need to have a smaller mesh. Also to capture the physics, the size of the mesh is transitioned from the ground because area of interest is up to the pedestrian height. So we have maintained a lot of cells from the ground in upward direction to capture that effect. And as you go up, the cell size keeps increasing. So and this, as Praveen said, there are a lot of guidelines about what should be the cell size to make sure that the CFD results are accurate, and we have followed those guidelines and validated kind of the accuracy of the result.
Sir, a small doubt. Does your tool take thermal comfort and solar irradiance into account?
Okay, so I am little okay. So that this question might be because of the last slide. So in thermal comfort application, yes. In pedestrian comfort application, no. So indoor thermal comfort application that we have developed, it takes care of all of this that you asked for. But for pedestrian comfort, we have not yet done any work on integrating the temperature effect on pedestrian comfort.
If I'm planning to make a large scale naturally ventilated buildings, like if I take a neighborhood and if I'm thinking to see the natural ventilation in, like, say 100 to 200 buildings together, like, does your tool support?
No, that is the created future for us. That is why you see these two applications separately now. One which talks about the outdoor wind environment and one which talks about the indoor wind environment. The created future for us is we'll combine these two so that we can take wind inside the building. Right now, we are not taking wind inside the building, if I may say so. But that is a future for us. That is where we are heading.
Do you recommend any solvers for the same, like any solvers like OpenFOAM or any solvers for solving this purpose?
OpenFOAM has the capability for doing it. Actually,
You said, yeah, you said it correctly. Any solver, yes. You can use any solver, yes. All of them can do it. It's a wind flow, and when you talk about natural convection, it is actually a effect of temperature on air. So there are a lot of modules available: Bosnius approximation or incompressible ideal gas, and so on and so forth. So these modules are already available in most of the solvers. I haven't seen kind of a CFD solver in which we cannot model natural kind of a convection.
I think we may have lost Vijay.
Yes. So meanwhile, I was quickly able to fetch a few clips of about the solar radiation in the UTCI questions. So Nathan, can I share the screen for a moment?
Certainly.
Okay. So as I was saying, this is the kind of work what we are trying to do. So for these buildings, we are trying to consider the outdoor solar irradiance, and then compare it with the wind and then form UTC. So this is kind of very research or work in progress kind of thing. So I just wanted to add this, and additionally the guidelines about the meshing or the CFD setup, you can refer to COST action 732. That is the best practices guidelines for such wind analysis. So COST 732.
All right. Well, thank you very much. And it looks like we're coming to the end of our hour. But Praveen, this has been a really interesting webinar. I also want to thank Vijay for his input. And thanks to everyone for joining this IBIPS USA Research Committee webinar. If you enjoyed this webinar, please consider joining the IBIPS USA Research Committee. Email research@ibipsa.us or visit the link in the Zoom chat for more information. For those of you joining us on YouTube, please like this video and subscribe to our YouTube channel. And to everyone, please join us again on November 18th at noon Pacific time, when Ellie Jungmin Han presents AirNet using 3D convolutional neural networks to estimate annual radiation intensities on building facades. Thank you, everyone. Have a good day.
Thank you.